So, because if we look into how data is typically written in a real world scenario, this is now a rough overview on how this works in Pick on GPU, but the same holds true for many codes. You might have very custom data formats inside your application that are tailored towards the specific needs of the algorithm and really fine-tuned complex data structures that your algorithm understands best or handles best, but might not be ideal for output. In the case of Pick on GPU, for example, the particles are stored as a list of frames, so there is not that single array of particles right in the beautiful way that we want to output it, but we need to prepare data first by concatenating, filtering particles, maybe computing the indexes anew, and then maybe doing a further conversion from AOS to SOA layout. And that can mean that we will have data copies, and we might wish to elide those data copies. And we can do that because, on the other hand, if we look at how I/O libraries optimize I/O, then one very simple trick that already probably gets you 90% of what you can get from I/O performance. And the simplest trick is really you need to do few operations, and those operations need to be big. So you tell the file system, okay, here are 5 gigabytes of data, deal with it. If you try to micromanage the file system by giving it a bit of data here, a bit of data there, then write a bit of data now, and many small operations, then your performance will be bad. But if you really want the file system to operate efficiently, data should be written in rather infrequent big calls, big operations. Now, that of course depends on how much memory you can spare to do that kind of thing. So it might not be totally possible, and in the end depend on the memory that you have available. But what especially ADIOS traditionally does in order to do that is it has an internal data buffer that it uses to serialize all the data into. So the data is first written all into memory before putting that entire chunk onto disk. We actually bugged them a long time to have also the option to write data to disk intermediately, because we just saw that especially Pick on GPU is memory bound, and we have had memory troubles working with ADIOS because this kind of aggressive optimization that they're doing works well for the file system, but only if you have the memory for it. So nowadays it's better, there's a better option for fine-tuning things. But still, ADIOS works with internal data buffers. So what you can do to elide data copies is, if you need to transform data anyway, if you need to prepare data anyway, then don't write it into a new buffer that you allocate, but instead ask the backend, hey, do you have a buffer for me that I can write into, and store data that way. And that's now what we, as a final step for the OpenPMD session, are going to add to the heat equation example again. So. There, I find the. So open exercise 15. Because we had a similar situation here actually. We downloaded data from the GPU, which did this transformation that elided the padding, because we don't want to store the padding to file. So we also have a kind of data preparation there. And instead of downloading that into the host buffer, we directly ask Alpaca to download the data into the I/O buffer of ADIOS. So if you open again the file openpmd output.hpp in exercise 15, the way to do that is to use the store chunk call that we have already been using, but this time to not specify any pointer, because we want to have a pointer from the backend. So the pointer is now the return value. And for this reason, since we don't specify a pointer as part of the command line the function arguments, there can be no inference of the data type, so we need to be explicit about that now. And we get back a buffer that points us directly into the internal memory of ADIOS. And what we can now do is we need to use alpaca create view to make this buffer known to alpaca. Then we can download from the GPU directly into the backend buffer by ADIOS. So we'll do just that. Now, one little thing that you need to pay attention to about this OpenPMD buffer, and the first time that I had this bug, it took me ages to figure out what was going on. Especially older versions of the binary pack file format in ADIOS, it might happen that there are internal reallocations while data is being written. So the pointer that you get at some point of writing this might not stay valid. And in order to fix that, I try to be explicit in the OpenPMD API at least, so that you have no way of making that mistake. So what you need to run first is OpenPMD buffer, which is the thing that we got returned here. And now let me hope that I remember the right API call. I have the... Yeah, exactly, here's the Doxygen page. The only thing that you can call on this item is the function current buffer, which only stays valid until you change something in the output. And that returns then a span-like type. So span is a C++20 standard library edition. We have a little subset of that class included into OpenPMD in order to support that. Span is just a view into memory held by someone else. So we call OpenPMD buffer.currentBuffer. We now have this view into data held, in this case by ADIOS. Let's look back into the documentation at what span can do for us. So it has some typical C++ functions. We just want to provide the pointer to alpaca again to make an alpaca buffer out of that. So we just need to call .data to get the actual pointer. And this is now an actual pointer that we can use to create an alpaca view. using the device that was passed as a function argument, def host, specifically pointer, the extent which we have from the GPU buffer, this one, logical extents. And since we have no pitch, we leave that out. So this is now the host buffer. Now alpaca mem copy, I don't remember the syntax for that one. The host buffer, so the destination buffer is first, right?
Yes.
Okay. Device buffer is called ACK buffer. Should be it, right?
ADIOS is missing, yeah.
Okay. So we need to wait on the queue then. Is it called dump queue? Yes. Alpaca colon wait, right? On the queue.
Yeah. And then the queue.
Okay, so let's try that. Maybe full screen. So this is the thing that we wrote. File system's giving us some time again.
It looks like the file system is quite
Yeah.
fast.
Wonder if we can do something about I/O performance. Now, is the application hanging or is it just being the file system again? I hope it is. Okay. Yeah, probably some job running again and using lots of I/O.
Can you explain again, so create view, what it does?
Create view tells Alpaca about what it needs to know about this buffer. Because we only have some pointer, could be anything, could be a GPU pointer, could be CPU pointer, could be whatever, could have this extent, that extent, could have a pitch or not. So in order for Alpaca to know what exact memory copy it needs to perform, it needs to know what kind of buffer this is, and we can do this by turning that pointer into something that Alpaca understands by calling create view. Okay, apparently things finished now. Should not have been that slow, but I'll blame the file system. So let's try that, and let's try dumping the data in order to see data was written. I could now try visualizing it again, but let's, as verifying that things are correct, I think I leave that as an exercise to you, hoping that the images will be correct. I tried it out for the official solution, which I put into folder 16, and there the images were correct. So if you want to verify it, you can definitely try. It looks roughly like the data that the heat equation would write from squinting at it. Otherwise, one thing that I think I forgot to mention, and I would want to make that explicit, because okay, it's good that we are approaching the end because my voice is leaving me. That I wanted to mention, because yesterday we switched from file I/O to streaming I/O by changing only the configuration. There is one thing about that I didn't tell you yesterday. I actually wanted to tell it to you, but let's do it now. Because that only worked because we wrote the I/O workflow in such a way that iterations are written at one point, then closed, and then never written again. Because by using streaming, we necessarily need to have some form of sequentialization of data into, okay, I now see this data and now it's gone. So data needs to come by iterations, iteration 1, iteration 2, iteration 3, and you cannot read iteration 1 after having read iteration 3 already. So you need to write your data workflows in a way that does not support random access in order to be able to stream. The way that we do this is by having this call write iterations, as well as on the reader side, we didn't see that one, read iterations. If you want to do random access I/O, what you would do instead then would be to directly access the iterations that way, for example, this. Then you get direct access, but then you will not be able to stream. And especially for writing, you will usually process your data in such a way that you have one iteration, then the next, then the next. So in writing, it makes sense to use this write iterations. In reading, it depends on your application because, for example, we looked into the OpenPMD viewer and it was nice that we were able to go back in time and go forward in time again. So there are applications where you want to have random access, while doing streaming I/O means that you have a more limited way in how you can interact with data and you see the data in a sequential manner. One project that I'm also currently working on is making those APIs here a bit more compatible with each other. For example, when you call close iteration down here, if you want to flush intermediately, you can also call something like mserious.flush. But close iteration also closes the entire iteration and sends it off to the reader, which means since this is currently written for streaming workflows, an iteration once closed cannot be reopened currently. I want to change that for the next release and I'm currently working on that. So the future API will be to merge that write iterations, read iterations, bare iterations thing into something shared for everything, where depending on what access type you specify, you can then reopen closed iterations, because this is also relevant for file I/O, where you want to close and reopen file handles. Yeah, so work is ongoing. This is the current state. The tendency should roughly be, if the workflow that you are pursuing is compatible with the streaming mode of operation, then also use write iterations and read iterations, these calls, that make sure that everything you do is compatible with streaming. Otherwise, do random access. Yeah, we're approaching noon. My clock and my stomach are telling me. So I'm done with what I have prepared for the workshop. I told you things about how to use OpenPMD and some of its environment and ecosystem and what options there are. If there are any questions, I think there were some questions on data modeling yesterday. Maybe now that we have looked at how to model mesh and model particle data, this might have already been clarified a bit. Otherwise, feel free to contact us and ask questions on what can be done. I hope this was you were able to somewhat follow me, and yeah, thanks for sparing me your time and listening to me.
You have some more minutes, I think.
So, only for the online audience and also for everyone here, we have this Slack channel where you can currently reach us very, very fast and interactive. We will try to have an eye on the Slack channel the next week. I hope the channel will still stay, because I read something that some license or what we're using is running out. But I think the channel should be open next week too. Okay.
Okay, also we have a Slack channel for OpenPMD, or here are some more pages.
Yeah. And additionally, since now we have some more time, Jürgen and I discussed that we not run the Pick on GPU session in parallel, but sequentially, so you don't have to choose in which room you go. We'll just keep it as a sequential flow of the talks.
Okay. I think lunch is planned for 12:30 or?
12:15.
12:15, okay.
But it makes no sense to start it. Half talk now.
Yeah, when do we meet again?
What's the schedule saying? I think 13:15 Central European Summertime. Is this correct?
1:15 would be lunch.
12:15 would be lunch.
12:15.
12:15 would be lunch, 1:15 would be starting again.
Okay, so we will meet at 1:15 or 13:15 Central European Summertime again in the Zoom.
Have a nice lunch break.